Assalamu alaikum and welcome to another session for EEE 6311. We'll be continuing with the same topic that we discussed in the last class. So we'll be actually having a little review on the topic that we discussed in the last class, that is on hydrothermal system economic dispatch, or where we considered that we have the presence of both thermal generation system and hydropower generation system, and both of them are contributing to a common load. So we started with the scenario where we were neglecting the losses. So this was the starting topic, and after some basic discussion on hydrothermal scheduling, the necessity of hydrothermal scheduling, we went on for the modeling of the short range hydro scheduling, and we covered the equation 4.65, which was the objective, our main objective function, because as we mentioned that in the hydrothermal there is no fuel cost involved. So if we are targeting to minimize the fuel cost alone, then we only have to take care about the fuel cost associated with the thermal plants. So f of pt, this was the fuel cost for the thermal power station. PT is for the real power output from the thermal station and at a specific time t. So if we want to get the whole cost function, then we have to integrate from 0 to the time spent under our consideration. So this was the objective function, and besides this we also have to consider the equality constraint. So one equality constraint is now that the real power output from the hydro and the real power output from the thermal at any specific time t, the summation of that should be exactly balanced by the demand. Of course, we are not considering any loss here. So another equality constraint was that how much how much water availability is there for that duration of time under consideration. That is for T amount of time, capital T amount of time, how much water is available for your hydropower generation. So we can only use up to that amount of power. Okay. So integral of W with respect to time, where W itself is the function of pH. So this is basically nothing but the input output characteristics for the hydropower generation, okay, W of pH, and we are integrating it for the whole time interval under our consideration. So then we discretized it and we went on through the derivation part for this. So this section was related to the case where no transmission losses were taken into account, and we found that we formulated the Lagrangian and we applied the necessary condition, that is the first partial derivative with respect to all these decision variables. Now we are considering different time stages, so k equal to 1 up to s time stages. So all these equations should be satisfied. That means the necessary condition should be satisfied for all of these time stages, k equal to 1 up to s. So we have a number of decision variables there because we are now considering each time instance separately. So pH k will be all the unknown decision variables. Similarly, ptk will be the unknown decision variables, okay, as well as the gamma, which is the conversion factor. This is another unknown variable. Similarly, the lambda, the Lagrange multipliers for each time stage, that would be an unknown variable. So what we said about gamma, we can see here that lambda is depending on the time interval, which is actually balancing, which is actually converting the equality constraint into the Lagrangian. Okay, so that means we are actually getting rid of the equality constraint by making the Lagrangian an unconstrained optimization problem. So for incorporating that particular power generation and demand balance, we incorporated this lambda, and because now we are considering kth time instance, so lambda will be for a different time instance, we might get different lambdas. On the other hand, gamma is associated with the conversion factor from water availability to fuel cost. So that gamma, because your head is constant, so your water head is actually considered to be constant. So gamma is actually independent of your time stage, okay, kth time stage. So gamma is fixed until and unless we have more than one hydrogenerating unit. Okay, so for any single generating unit, hydrogenerating unit, you have single water head available, and for that single water head availability, you have only a single gamma to be considered. So with respect to all these decision variables, we took the partial derivatives and we formulated all these equations starting from 4.73 up to 4.76. And then we simplified it. After simplification, we found that, well, we got 4.78. So we found this expression here, that is df over dpt equals gamma into dw over dph should be equals to the same value of lambda. And then we took the incremental model. If you take the incremental model, then we also actually found out the physical significance of gamma, that is nothing but a conversion factor. Okay, so gamma is nothing but the conversion factor which converts your water consumption into some sort of fuel consumption, equivalent fuel consumption, you can say. So then I actually skipped this part, and today what we will do, we will be going through this skipped part in the last class. Okay, so we'll be taking one example today of how to solve this hydrothermal scheduling problem. And before doing that, we will go through a small algorithm which is discussed in this book in these 4 steps, and we will be going through example 4.7. And after that, actually in the last class, what we did, we skipped this 4.7 and the specific and the associated algorithm. Rather going there, what we did, we actually went through this 4.6.2 article and we finished this topic also. So in today's class, actually, we'll be focusing mainly on solving this problem and the associated algorithm. So let's start with the problem. Okay, for algorithm first. So now in the hydrothermal scheduling problem, because it is a short-term hydrothermal scheduling, so it can, the time span under consideration can vary from 1 day up to 1 week. So here it is taken, let's say for example 1 day, that is if you consider it into hours, then it would be 24 hours. Now if the given water consumption is high, the hydro unit can produce a larger power output. Of course, if you have higher head, so that means if your head is higher, water head, water height, you have high water head, this is H, this is H1, and let's say this is H2. Of course, for H2 you will be getting mgh2, whereas for H1 you will be getting mgh1 amount of potential energy. And of course, because m in both cases, m and g values are the same, water mass and the gravitational g values are same. So only thing that differs from this one to this one is the values of h. So if h increases, your potential energy is higher. So potential energy 2 greater than potential energy 1. So that means if you have higher head available, you have more potential energy that could be converted into the kinetic energy. So in this case, if the conversion factor is constant from potential energy to kinetic energy, considering the losses, so in that case, you will have more kinetic energy available that would ultimately produce your more output power. So if this is P2, this is P1, that is real power, so P2 should be greater than P1. So that is quite natural. So the value of gamma, that is actually the conversion factor, this is actually one of the unknown variables in this case. So here this paragraph basically is discussing how we actually how will we actually continue our solution for an unknown values of gamma, where the gamma value has to be updated throughout the algorithm. Okay, so in this paragraph they are giving a short note on how to actually go with the values of gamma, with the updating process of gamma. So if you have higher, for any specific value of gamma, for any specific value of gamma, that is the conversion factor. Okay, so this converts your water value or consumption of water into corresponding fuel consumption. So so if you have higher water consumption, you have higher power output to meet the load demand. So in this case, what we will do, okay, throughout our iteration, what we will do, the detailed algorithm will be discussed later. Here, they are simply giving you a little glimpse of what is going to come next. So if you have higher water consumption, then higher output could be met. So in this case, what it means, basically, it means that you could do well with a smaller value of gamma. Okay, because probably it means, let's say, for gamma equals to something like, let's say, 0.5, your water consumption is calculated as, let's say, 1.5 into 10 to the power 6, something like that, meter cube. This is your water consumption. Whereas to satisfy the specific demand at that time stage, your available water consumption, is, let's say, 1.4 into 10 to the power 6. So as we took this value of gamma, we came up with some value of W, or the water consumption, which could meet higher load demand. Okay, but actually you don't have this much of W consumption available. Your available water availability is this much. So that means with this value of gamma, if let's say we started with some arbitrary value of gamma, any iterative process, we have to start from some assumption. So with this assumption, starting assumption, let's say if we find something like this as the final outcome, we check with our water availability. This is our water availability. So they are not matched. That means you have to update your gamma now. Okay, so you have to update your gamma. This gamma is not acceptable, because with this gamma you are consuming, you are saying that, well, I need this much of water consumption, but unfortunately you only have this much of water available throughout that hour or throughout that day, because water level availability is constant, the head is constant as per our assumption for short time hydrothermal coordination. So that means now these values are not matching, so we have to play with this gamma, we have to update this gamma. Similar case, if let's say for this gamma we had found, let's say for example, instead of 1.5 into 10 to the power 6, let's say we found 1.3 into 10 to the power 6 meter cube, which is also not equal to the water available. So in this case also we had to update this value of gamma. So so the update should be such that whatever difference we had at the first, with the first assumed value of gamma, in the next iteration with the updated value of gamma, this error value is minimized in both ways. Okay, be it positive error, be it the negative error, in both cases the gamma value should be updated in such a manner that the error value is minimized. Ultimately our target is to find out such a gamma value which will almost balance out this water availability amount of 1.4 into 10 to the power 4 meter cube in this case, for example. So this is more or less what we are going to do. So now let's see what are the specific chronological steps in a better way, stepwise. So so this is the calculation procedure for hydrothermal system. ED, of course, without network losses. Of course, without network losses. Now, given an initial value, so that means some value should be given or some value should be chosen. Okay, if it is not given, it should be chosen. So given an initial value of gamma, we start our iteration. Let's say iteration counter is denoted by k equals to 0. Compute the power distribution for hydrothermal system for all time stages. That means k equals 1 up to s according to equation 4.77. So the equation 4.77, that means if you know the value of gamma, it means in the next step number 2, you should be able to calculate this 4.77. So let's see. So if you have this gamma chosen, arbitrarily chosen, then what else do you need? We need the FK, that is the fuel cost function for the thermal plant. We need to take the derivative of that, first derivative. Also, we need the information about the hydro unit input output characteristics. So we need the specific mathematical model for the thermal unit cost function, fuel cost function, and we need the hydro unit input output characteristics function, mathematical function, mostly quadratic function that we are actually taking into account in this course. So besides gamma, we need to have this fk value for kth instance and wk value for the kth instance. So hopefully those, of course, those will be given for a given problem, for a specific problem. So once you set gamma, then you know fk and wk expressions for kth time instance, then of course you can compute the power distribution for a hydrothermal system for all time stages. We'll see in the example how we are going to do it. Now, once you know your distribution of power, means how much hydropower should be taken and how much thermal output should be taken. Once you calculated it, then you will be in a position to calculate the total water consumption, WK, for this specific gamma that you chose arbitrarily. Now we have to check that, well, this WK for this specific gamma, whether it is within a certain limit or whether it is within the close vicinity of the given water consumption W sum. This is the given water consumption. So just as I said, it is, let's say 1.5, okay, 1.5 10 to the power 6, something like that, meter cube. So you're calculating your gamma, you're calculating your power distribution, PT and pH, PT for the thermal unit, pH for the hydro unit, and then using those values you are calculating the water consumption for this gamma. Then you check the error. If the error is within a tolerance epsilon, then you stop. Otherwise, what you do, you have to update your gamma. So the main points are here. If WK is greater than W summation, that means for a specific value of gamma, you calculated W and you compared that with your given water consumption W summation. If this condition is satisfied, this means the gamma that you chose is too small, and that's why actually you are requiring more water. Your outcome says that you have to use more than required water, more than the available water. So your conversion factor is actually small. So you have to increase the conversion factor so that this calculated water consumption comes closer to the available water consumption. Okay. So how do you update the gamma? The gamma has to be updated. You have to increase the gamma. Okay. And vice versa. If WK is less than W sum, means the gamma that you took initially, that conversion factor, that is too high. That's why the value calculated, W value, is the outcome of the calculation is small compared to the available water. So in that case, what you have to do, you have to reduce the gamma value. So gamma k plus 1, that means the updated gamma should be less than the previous gamma. And then go back to step 2. Okay, so with this updated gamma, you go back to step 2, you recompute your power distribution, recompute your total water consumption, recheck this error, whether it is less than epsilon or not, and this will be the looping. So in this manner, the algorithm will continue, and hopefully it will converge if everything else is correct, if your calculation and other things are correct. So in the book, actually they have mentioned that you have to update the gamma, but there is a small problem. They haven't mentioned any specific way that how much increase you should do here or how much decrease you should do here compared to the previous iteration gamma k. That means, let's say if gamma you choose as 0.5 and you find that this condition is true, so how much should you increase? Should you make it 0.6 or should you go for 0.51 or 0.505 or how much? So there is no clear indication. So that's why we will be using for this specific part of updating gamma, we will be using a little bit different algorithm only for this updating part. Okay, for gamma, remember the other things would be same. Step 1, step 2, step 3 will be exactly same. Step 4 will be same partially, except this part. Actually here they haven't given any indication of how to update it in their example. So what I would share with you is the specific way of updating this gamma, and we will call it as the gamma iteration algorithm. Okay, the gamma iteration algorithm, and we'll be applying that algorithm here in this example 4.7 for the solution of this problem. So let's start with the problem statement. So as I said, we have, okay, so in this example we have one thermal power plant and one hydropower plant. The input output characteristics of the thermal plant is this f. So this is like a quadratic function. The input output characteristics of the hydro plant, it is also quadratic in nature. The fuel cost function for the thermal plant is purely the function of the real power output from the thermal plant. At the same time, the W value, that is the input output characteristics, that means the pH is actually determining how much water consumption will be required. Okay, so W is basically a function of pH. So with this basically the input output characteristics, and if you want to, let's say, plot it, it would be something like this. So your input would be in the y-axis, output would be in the x-axis, and it is a quadratic function, something like this, almost identical to your thermal power plant F and PT. So almost identical, something like this. The daily water consumption, actually this is required at this step, important step of convergence checking. So the W summation is given as 1.5 into 10 to the power 7 meter cube. So this value will remain constant throughout your time span of calculation. Then they are giving you the load demand, the daily load profile for 24 hours. And it is something like this. So this demand says that, well, so the x-axis reads the hours, 0 from 24, starting from 0 up to 24. And the y-axis values of the load values, these are in megawatts. So starting from hour number 1 up to hour number 8, your load remains constant, is 350 megawatt. From hour number 8 up to hour number 18, so at hour number 8 there is a jump, and up to hour number 18 that value goes probably around 680, something like that, and then it goes down, and probably it is something around 500 for the remaining part of the day. So it is from hour number 18th to hour number 24. So although it is a 24-hour load profile, you can clearly see that there are actually 3 different time stages. The first time stage is starting from hour 1 to hour 8, the load remaining constant. Second time stage from hour 8 to hour 18, load remaining constant to another higher value. And from hour number 18 to hour number 24, the load goes down to some intermediate value of 500 megawatts. So in total, there are 24 stages, but actually we can also consider that there are 3 distinct time stages of 3 distinct load values. Okay, well, so then the power output limits of the thermal plant. So this is the lower limit and this is the upper limit for the thermal plant. Then you have the lower limit as well as the upper limit for the hydro plant. Now the question is, you have to determine the economic dispatch for this hydrothermal system. Okay, so what to do? So what we have to do first, we have to calculate with the help of the input output characteristics. So the input output characteristics is this F. So what we can do to start with, we can calculate what is my dF over dPt and what is my dW over dPh. So dF over dPt would be how much? So if you take this, it would be 0.0007 pt plus 0.4, and this would be 0.003 pH plus 0.8, and they will be related by this expression dF over dPt equals gamma into dW over dPh, and that should be equals to lambda k. This is the hydrothermal coordination relationship already derived. So so this is what we will do now. So this is what is actually done next. So what you will see, basically you will see the expression like this: 0.0007 pt plus 0.4, then that should be equals to gamma multiplied by 0.003 pH plus 0.8. Okay, so this is one of the equation that should be true. Okay, and that should be equal to lambda k, where k equal to 1, 2 up to s. So this is one equation. Another equation is, of course, your power balance. So in the power balance equation, what do we have? In the power balance equation, we say that, well, PHK, that is hydropower output at the kth instance, plus PTK, thermal power output at the kth instance, minus PDK should be equals to 0. That is our power demand balance, power generation and demand balance equation. So you can see, well, we can also write it as K simply, because that should be true for all K. So we can add this additional term K here. So now you have two equations. You have two equations in terms of PTK and PHK here, and PHK and PTK. Remember, PDK is the demand which is given. So this is given. So you have two equations and two unknowns. We can solve it. Okay. So now let's go to the whiteboard. Yeah, let's go to the whiteboard and try to show the derivation there. Okay, so what do we have? So we have two expressions. Let us rewrite those expressions. 0.0007 PTK plus 0.4 equals gamma 0.003 pH plus 0.8. This is one equation. Second equation is PHK plus PTK minus PDK equals to 0. So there could be many ways to find out the expressions for PTK and PHK. There could be substitution process, or we can form the matrix and you can take the inverse of the matrix and try to find out the expressions. Ultimately all the same. So if I go for the simplest one, the substitution process, so what you will do, let's say we want to substitute PHK by PTK and PDK. So if I replace it here, so I will get 0.007 PTK plus 0.4 gamma 0.003 PHK. So this is K. So this is PDK minus PTK plus 0.8. Okay. So then bring all the PTK on one side. So this is PTK plus 0.003 gamma PTK equals 0.003 gamma PDK plus 0.8 gamma minus 0.4. So now you can take what is PTK. This is 0.003 gamma PDK plus 0.8 gamma minus 0.4 divided by, sorry, should be 7, 0.0007 plus 0.003 gamma. So now you can see, well, this PTK can be expressed simply as some function of gamma and some known values of demand at the kth time stage. So if we can choose gamma, if you know the demand, you can have some PTK. Okay, then you will get the values of PTK directly. So now if I replace this value of PTK over here, then I will get the PHK. So PHK would be simply after the replacement and some small manipulation, you will get 0.8 gamma plus 0.4, 0.0007 plus 0.003 gamma. So again, you can see, well, PHK also is now depending on only the known values of demand at the kth instance, kth time stage, and some iterative value of gamma. So because we don't know gamma, so we have to assume this value of gamma now. And with that assumption, starting assumption, we will calculate PTK and PHK. Okay. Once we get those values, then we will be in a position, if we get PHK, once you know PHK, we know that W, the water consumption, is purely the function of PHK. That is the input output characteristics for the hydro unit. So this is also given, and that is, let's say, 0.0015 pH squared plus 0.8 pH plus 2. So means if you know, so let's say this is PHK, this is PHK. So if you know PHK, you put it back here, and you know what is your water consumption. Okay. If this water consumption is different than your given water consumption, then update gamma. And this is the iterative process. So next we will tell after this how to update that gamma. Okay. What is the process for that? So let's erase everything. Okay. So now let's say you have chosen some value of gamma as given in the book, that is gamma equals to 0.5. So for gamma equals to 0.5, what do we have? We have 3 time stages. Okay. K equals to 1, K equals to 2, K equals to 3. 24 hours, but 3 time stages. So what are the values of PTK and PHK? So if I calculate for this gamma, for K equals to 1, what is my demand? For K equals to 1, the demand is around 350. So for K equals to 1, PD1 is actually 350. So K equals to 2, PD2 is probably 680. Probably all these in megawatts. And K equals to 3 is PD3. Is how much? It is around maybe 550. Okay, we can check the book estimate. Check the book. So Okay, it is 700, 500 and 350. Yeah, so these are basically 700 given in the book. 700, this is not 680, this is basically 700, then it is 500 and it is 350 is correct. So in this first stage, how many hours? 8 hours. So here I have 8 hours span. 700 megawatt, how many hours? 10 hours. The third stage is 6 hours. So that gives you 24 hours of distribution. Okay. Okay. So now for k equals to 1, my load PD is 350. So I calculate my PTK and PHK. So the calculated values would be, as per the book, it is 238.6364. For k equals to 2, it is 477.2727. And for this one, it is 340.9091. PHK 111.3636, 222.7273, 159.0909. So as I know now PHK, so I can calculate my W consumption or W summation, how much. So that would be, you have to take care of the input output characteristics for the hydro unit. So that is 0.0015 multiplied by pH1 squared. So that is 1100.3, let's say 36 squared, this value, plus 0.8 into 111.36 plus 2. So this is the cost function. Now this k, the k equals to 1, this contains how much duration? What is the duration here? So the duration here is, just let me check again the book. Okay, the duration is 8 hours. Okay, so just confirm duration is 8 hours. So duration is 8 hours, and within these 8 hours you have, in each hour you convert it into seconds. So this is your conversion factor for seconds. So then you have k equals to 2. So this is your hours and this is the conversion factor for second. Because ultimately what we want it in meter cube. So this value is the water usage or water availability. So to produce this much of PHK, how much water is required? This is in meter cube. So then for the k equals to 2 value, we continue in the same manner, multiplied by how much? 222.72 squared plus 0.8, 202.72 plus 2 into 8 into, sorry, this is not 8. How many hours? This is 10 hours. So 10 hours into 3600 plus 0.0015 to 159.09 squared, 0.8 into 159.09 plus 2. This is for 6 hours. Convert into seconds. So now if we add up everything, so you will have the value as 1.5937. This is the value 1.5937 into 10 to the power 7 meter cube. Whereas your given W Given W is how much? Given W is 1.5 into 10 to the power 7 meter cube. So you can see that with this gamma equals to 0.5, we calculated all the values for 3 time stages, and then we took care of the duration of each time stage. These are the duration for each time stage. First time stage is 8 hours long, second time stage is 10 hours long, and third time stage is 6 hours long, multiplying by the conversion factor to make it into meter cube. Okay. Okay. So this value is different than this. And different in what sense? This is higher than this. Means your gamma value is small, your conversion factor is small. Because of this low conversion factor, you are requiring to satisfy this demand. Okay, this demand of 350 megawatt for 8 hours, 700 megawatt for 10 hours, 500 megawatt for 6 hours. You require more water than your available water per day. So what you have to do, you have to increase this gamma. How will you increase? This is the main thing here. This is where the discussion of today's class differs from the topic exactly given in the book, because no specific way is discussed in the book for this. So let's say now, how would we take the value of gamma and how would we update the values of gamma? So one thing is sure, that this value is greater than this. This value is greater than this. Okay. So we need to update the gamma value. So we need to increase the gamma value so that this value comes down. This value comes down. You need to increase the conversion factor so that with higher conversion factor, your water usage requirement will be less. And this is our target. So that means in this step, we have to take some gamma value which is higher than 0.5. Okay. So here what we will do, we will take a pretty comparatively large value of gamma such that the W calculated for the new gamma becomes lower than this. Again, we'll take another gamma value now, which should be higher than 0.5, and it should be such a high value that when we calculate the W with that new gamma value, the calculated W value becomes less than W given. Means if this is your W given for gamma equals 0.5, you are here. Okay, sorry, 0.5, you are higher, not lower. So this is the scale. Let's say this is your scale. So this is your gamma 0.5. So for gamma 0.5, you get some W, which is, okay, this is your line, W given. This is your target line. With gamma equal to 0.5, with gamma equal to 0.5, what we get? With gamma equal to 0.5, we get some value which is higher. So we have to update the gamma. But before updating, remember, before updating, we take another value of gamma, which will give us some W here. Here or anywhere less than the W given. Okay. So this is our next point. So if we take that, let's say we choose some value which is gamma equals to 0.6. So with gamma equal to 0.6, what we have to do, you have to recalculate all these things. Gamma equal to 0.6, you have to recalculate all of these things. Okay. So with gamma equal to 0.6, what are the things that we will get? we will get, let's say, PT, let's say 284, 536, 392, PHK is 60, 66, maybe 164. You can calculate it, 108, something like this. With those values, with this updated PTK and PHK, you will do the same thing. That means you will recalculate W sum or your W required, and this will be 1.03 into 10 to the power 7, of course, meter cube. Okay, so this is what you get. So you see, we have reached our target. We have arbitrarily chosen large jump from 0.5 to 0.6. 0.1 jump is actually a large jump, remember, for this kind of scenario. So with that, we have got, let's say, for gamma equal to 0.6, that was for 0.5. Neither of these is correct. Okay, neither this nor this is correct. So what we will do, we will calculate a new, okay, so now with the iteration starting, what we will do, we'll recalculate some gamma, which is basically some average of this gamma 0.6 plus 0.5 divided by 2, which is 0.55. Okay. Okay, so let me make this diagram a little bigger so that it will be easier to understand. Let's make it a little bigger. Okay, so let's say this is your 0.6 gamma. For 0.6 of gamma, you are getting this W. This is your target, and this is, let's say, your 0.5. This is not to the scale, remember, this is not drawn to the scale. So we are calculating a new gamma, which is some average of these two, 0.55. And with this, of course, we can calculate new PT, K, and PHKs, right? So let's see what are the new values. So the new values would be 87.234, 191.489, 131.914, and this one will be 262.766, 508.5106, 368.0851. Okay, and in this case, the calculated W sum is 1.285 into 10 to the power 7. So with the average of the first two gamma, that means this is for gamma equals 0.55. For gamma equal to 0.55, this is this. For gamma equal to 0.6, how much was, it was, W was 1.03 10 to the power 7. For gamma equal to 0.5, how much was W? It was 1.5937 10 to the power 7. Okay, so for these three gamma, this one, the first one we took, we found it is greater than this. We took some higher value of gamma intentionally. We found that this W value is less than W given. We took the average. Okay, we took the average of these two. We found it is 0.55, and we see that we still have, this is very, very important, this step, understanding of this step for this iterative algorithm. With this updated averaged value of gamma, the W used or W available or W usage, it is still less than this. It is still less than this. So what we will do, We will now say, well, we will forget about this value. We'll update gamma equal to 0.55, 1.285 into 10 to the power 7. Okay. And now we will take the average of these two. So it will be 0.5. So that means the 0.6 with 0.6 gamma 0.6 we got much lesser consumption. With this updated gamma, the averaged gamma for 0.6 and 0.5, it became 0.55. Whatever water consumption was there, it is closer to my given W. So that my actual gamma will not lie, actually will not be near this value. Okay, it will be, of course, somewhere in between 0. Let's say 0.55 and 0.5. Okay, because you can clearly see the difference here. With 0.5 I am getting this, with 0.55 I am getting this, but with 0.6 the difference between this and this is much bigger. So that means my, probably this is where I did a mistake, 0.5, it should be 0.5, sorry. For 0.5 I have W value higher, 1.59. For 0.6 I had smaller value, 1.03. Okay, 1.03, this value. Now 0.55, average of these two I am getting somewhere here, let's say 1.28. This is 0.55. So means this value is actually not required. In the next iteration we will not require this value, rather instead of this value of 0.6 our gamma will be this, and we will take average of these two next, 0.5 and 0.55. So 0.5 and 0.55 divided by 2, whatever value comes, we have to recalculate with that value of gamma. We have to recalculate PTK, PHK, we have to recalculate W, and we have to see that with that W, what is the sorry, with that gamma, what is the W value and what is the difference in error? What is the difference in error? So in this case, what was the difference in error? So 1.5 10 to the power 7 for gamma equal to 0.6, the error is this much, 1.03 10 to the power 7. Okay, so it is like 0.47 into 10 to the power 7 meter cube. Okay, with gamma equal to 0.55, so it is a positive error. Remember, this is a positive error, positive. 0.55, 1.5 10 to the power 7 minus 1.285 to 10 to the power 7. So let's say it is 1.29. If it is 1.29, then it is 0.21 into 10 to the power 7. It's still plus, but less than this. The error is still plus, but less than this. So our new gamma will be this. That is to be averaged. That is to be averaged. With which one? With this one, sitting at the top, 0.55. Okay. Whereas in this case, what is the error? For gamma equal to 0.5, the error would be negative because it is 1.5 into 10 to the power 7 minus 1.59. Let's take 1.59, this one, into 10 to the power 7. So it is minus 0.09 into 10 to the power 7. This is negative. So if the error is positive, so in a nutshell, if the error is positive, like this, so what you have to do, you have to reduce the gamma. So you see we are reducing the gamma. If the error is negative, we have to increase the gamma. And we have to take the averaging. So let's see whatever is discussed here. I have put it into a code. So now I will go into the code and I will shortly show you that how the steps are actually being done. Okay. So this is actually your gamma iteration algorithm. So what will happen? Let's say in some iteration you may find that, well, that the error is negative but higher than this. So in that case, you have to reduce this. The gamma will be it will come here. Okay, 0 0.5, 0 0.55. So maybe it is 0 0.52, something like this. So in this manner, slowly this difference, remember this is your actual W given. This is your updated gamma. This is your updated gamma. So you are actually updating this gamma and this gamma. You are averaging them in such a manner that the difference between this gamma and this gamma is getting closer. So your convergence criteria would be, you will simply see that what is the difference between these two gamma. What is the difference between these two gamma? And hopefully with the increased number of iteration, this difference will diminish, and your W consumption for a certain gamma, your W consumption will be pretty much near to the W given. And that is the target. Let's see the thing that I just discussed in a code. Okay. So let's stop it. Stop the share and share a screen, the MATLAB. Okay. So it's the same problem. This is the hydrothermal gamma iteration algorithm. So these are the given values. W sum is 1.5 10 to the power 7. These are the alpha, beta, gamma. Remember, this gamma is not the gamma of conversion factor. This alpha, beta, gamma, simply I have given them some constant coefficient names. So this is basically, you can say, this is associated with your PT function ft, and this is associated with W. Okay, so it is like quadratic function. Okay, so alpha pt squared plus beta pt plus gamma. So we can say alpha t, beta t, gamma t, something like this. Okay, this is not, this gamma is not the gamma iterative gamma. This is the gamma of this function ft, and this is the gamma w. I'm saying this is the gamma present in W. So these are taken from the functions given f and w. These are the minimum and the maximum, minimum and maximum limits. These are the demands. Okay, we have 350 megawatt for 8 hours, 700 megawatts for 10 hours, 500 megawatt for 6 hours, and I have taken initially two gammas. Okay, two gammas. One is 0.5, which is given in the book. Another one, as I just showed, 0.6. Okay, so then I calculated, and I've given them two names. Let's say gamma H and gamma L. So gamma L is 0.5. So with 0.5, we calculate PHL, PTL, that is the hydro power for gamma L. That is the thermal power for gamma L. Similarly, hydro power for gamma H, thermal power for gamma H. Okay. Okay. So then once we calculate this PHL, PTL, PHH, and PTH, we can calculate the total water consumption for gamma L, water consumption for gamma H. How much are they? Let's see. So let's run it. Okay, so there's a debug mode. So let's run the code. Okay. So once it is run, so you can see what is W sum L. It is 1.5937. That is for gamma L, that is 0.5. W sum H is 1.03 10 to the power 7. That is for gamma 0.6. So these two values of W are on either side of our W available. That is 1.5 10 to the power 7. Okay. So we are in a target. So with these two values of gamma, what we are doing now, we are entering into my iteration conditional statement. So this is epsilon, this is the convergence criteria. So what is the convergence criteria? Epsilon. What is this epsilon? This is basically the difference in the gamma values, gamma H minus gamma L. So until your gamma H and gamma L difference is less than epsilon, you do this looping. Okay. So this is the actually the condition. So epsilon is taken very, very less, 0.0001. That means gamma H, gamma L values should be pretty close to each other before your convergence. So then what, as I said, I am calculating gamma M, which is gamma H plus gamma L by 2. So your gamma M is 0.55. With this gamma M, I'm calculating pHm and PTM. That means pH for hydro with gamma M 0.55, PT for thermal with gamma 0.55. So when these are calculated, so now I can calculate W sum for gamma M, that is 1.285, which is of course higher than 1.03. That means it is closer to your actual W. So now this is the condition. If W sum M, what is W sum M? W sum M is the available water or water required with gamma M, that is the averaged gamma calculated at the starting of the iteration. So if W sum M is greater than W sum, that is your given W, 1.5 10 to the power 7 meter cube. If this is the condition, then you update your gamma L by this gamma M, which you calculated at the start of this iteration. So you update gamma L. Okay. Else, if your W sum M that you calculated here is less than W sum, then you update gamma H by the calculated gamma M. So that means either you are updating gamma L by this new gamma, averaged gamma, or you are updating gamma H by this averaged gamma, depending on this condition. Okay, either this condition or this condition. Of course, any of this will be true for a certain iteration. And that ends your if else statement. And this is the final end for your while loop. So then this is your first iteration, and we continue because still my gamma M, gamma H is 0.55, gamma L is 5. Remember, this gamma H is updated after this if else condition is checked. So gamma H is no more 0.6, it has reduced to 0.55, whereas gamma L is still 0.5. So now in the next at line 26, when we will loop back, you will have gamma H as 0.55 and gamma L is 0.5. So you are updating gamma M actually. Okay, you are also updating gamma M now because you have new gamma H and old gamma L. Okay, reduced gamma H and unchanged gamma L. So your gamma M would be affected. So how much affected? Let's see. Actually, 2 iterations have been gone. So okay, let me start again. 2 iterations. I clicked it twice actually. So let's start again, start over again. This iteration. Okay. So this is your first iteration. Now we check gamma M. So your gamma M should not be 0.55, should be less than 0.55. So you see you have new gamma. And once you calculate everything, your depending on the condition, you will see that, well, your gamma H is 0.52, gamma L is still unchanged. Okay, so again gamma H is updated because probably, yeah, this condition is satisfied. Your W sum M is still, yeah, 1.43. okay, you see. So with gamma M 0.525, your W sum is still less than the W available, that is the 1.5 10 to the power 7. So what you have to do, you have to update gamma H. Again, we run another iteration. What is your W sum? Now it is bigger than your W available. So what you have to do, you have to update gamma L. So you see gamma L is no more 0.5, it is updated, whereas gamma H is to its value of its just previous iteration, immediate previous iteration. So your gamma L is updated. In this manner, we will keep on updating. Now what is W sum? It is again less than W sum, W available. So you have to update gamma H. So you see gamma H is 0.5188. And in the meantime, what you can see, we are actually closing up the gap between W sum M and W sum. Keep track of this. 1.49, you see, it is getting closer to W sum. 1.5006 is still your gamma H and gamma L value are not close enough to complete the convergence. Okay, so probably after 9 or 10 iterations, your system will converge, and you see your gamma M and gamma H and gamma L are pretty close, 0.5142, 0.5141. And of course, your W sum, that is your final W with gamma M, is also pretty close to your W, actual W, that is 1.5. Where is that? What value we have mentioned? Yeah, that is W sum. That is 1.49. Okay. So finally, actually, what we have done, we have updated the W sum. That's why the value is changed. So this should be 1.5 10 to the power 7. So you don't have to update this one. Just comment it. Okay. So the final W sum M would be your actual. Okay, we can give it a different name because that is your W sum. Okay, let's give it a name, calculated. Okay, this is your W sum calculated, and the W sum given is 1.5 10 to the power 7. Okay, so now if we simply run it, so now you can see one W sum M is 1.4999, almost exactly balanced by W sum. So this is how you conduct the gamma iteration algorithm. And please go through this lecture. I'm done for today, and this is the part I wanted to cover up to mid. This is the last part, this example problem. So you go through the lecture, and please, if you have any question, you can come up with the question. If not possible within one day, then of course before exam we can have a sitting. Okay, if you have any question, we can also do it online. Okay, so wish you all the best and see you inshallah. If you need any time for sitting, if you need to sit for the exam queries and exam related questions or anything you don't understand in this online video lecture, so please give me a knock in the group. We have a group, so I will be more than happy to answer. Okay, so thank you very much. Assalamu alaikum.